Looking at electrolytes and non-electrolytes. I'm guessing you've heard this term before, at least electrolytes. You know, if you look at Gatorade, and they always have the little gimmick of contains electrolytes. So what does that actually mean? All that means is that it actually contains ions. And for Gatorades or other sports drinks, those ions are usually potassium and sodium and magnesium. Those are the important ones for when you're working out so your muscles don't get cramped and you stay hydrated. Electrolytes are just ions. Why do we call them electrolytes? Okay, electrolytes now can conduct electricity. Strong electrolytes are those that will completely dissociate in water, meaning that they'll break apart completely into their ions. Some examples looking at sodium chloride, table salt. That will completely dissociate and you'll get all ions. Ions conduct electricity. If it's a strong electrolyte, this bulb is going to light up very brightly because you have all these different ions in solution. Let's now compare that to a weak electrolyte. These are some that will break apart into ions, but a lot of it stays on the reactant side too. So looking at this first one, if you have HF that reacts with water, you end up with these ions in solution, but as soon as these ions form, they end up going in the reverse reaction where you end up with HF again and water. At any given time you have roughly half ions and half molecules. Therefore, it can still conduct electricity, but notice the bulb now, much dimmer. So not as much electricity can be conducted, so then therefore a weak electrolyte. Big hint with these, if you see an arrow going in both directions, you know it's a weak electrolyte. So you're not going to have nearly as many ions in solution. Let's go to a non-electrolyte. These are things that can still dissolve, but they're going to stay together as molecules. So it won't be just a big clump of molecules all stuck together. When it dissolves, it breaks apart into the molecules. Sugar is like this. If you look at the example down here, here's sucrose, sugar, and it starts out as a solid. You add it to water, and now you have an aqueous solution of the exact same molecule, but still in the molecular form. If you look at our picture, notice the light bulb doesn't light up at all. We don't have any ions in solution. This is considered a non-electrolyte. Again, here's looking at the sucrose being dissolved in water. It's still dissolving. You no longer see it, but that is because each one of these molecules breaks apart. So this is a big clump of molecules all stuck together. Over here you see that each molecule is hydrated. It's surrounded by water molecules, but there's no ions. Giving you the breakdown of just definition and some examples of electrolytes and non-electrolytes. If it's strong, you have complete dissociation, which means that it completely comes apart into ions. And those conduct electricity very strongly. Weak electrolyte, weak currents, so they weakly conduct electricity. Here you have a mixture of molecules and ions. Non-electrolyte, things are dissolved. There's no dissociation, so they stay in their molecular form. Okay, let this be your did you watch it question. If this is the first one, if it's a strong electrolyte, that means they're going to have complete dissociation, so you can cross out the first one. That's not going to be it. So going between the next two, you got to be careful. You got to recognize the difference between them. Calcium ion looks exactly the same. The difference comes in the chloride ion. If you look at number 2, Cl2 would not be an ion. That would be a molecule. But it has to be number 3. For B, once again, this is a strong electrolyte. You got to be careful with these because, yes, it's going to dissociate, but does it dissociate into its ions? Do all of the atoms separate out? What happens? Once again, hopefully you can cross out number 2. We know it's not going to be that one. So it's between 1 and 3. If it dissociates into its ions, you have to recognize that there's a polyatomic ion in here. PO4 is going to stick together. That in itself is an ion. So this is still complete dissociation, but just into its ions. Okay, now let's take a look at doing a little bit of calculation with solubility. For something to be saturated, it is going to contain the maximum amount of solute in a given amount of solvent. The solubility of something, how much solute can you dissolve in a given amount of solvent? Our expression, given right here, grams of solute all over 100 grams of water. We usually measure it in 100 grams of water. That's our standard. And remember, 100 grams of water is the same as 100 milliliters of water. And water, why do we use water? Well, that's our universal solvent. It's the thing that can dissolve more things than anything else. So unsaturated solution, this now contains a lot less solute than can be dissolved. So in other words, if you take like a little teaspoon of salt and put it in a 10-gallon bucket full of water, you know that you could add more salt and it's going to dissolve. That would be an unsaturated solution. You could keep adding salt and it would keep dissolving. That would be unsaturated. Go to saturated solutions. This is where the water or whatever the solvent is cannot dissolve anymore. So it's maxed out for the saturated solutions. How do you know? Well, let's go back to our scenario of salt and water. If you keep adding salt, eventually you're going to get to a point where the salt settles out on the bottom. You could stir it up as much as you want, but it's not going to dissolve. Then you know you have a saturated solution. On the bottom here, it's kind of giving you the chemistry of it. So you start with that solid solute, it dissolves. Once we hit that saturation point, then it's going to stay crystallized, or it'll start crystallizing and going back to the solid. If you see something left over in the solvent when you're making the solution, you know it's saturated. It can't do any more dissolving. The first one is showing you just putting a dab of salt in solution. The unsaturated solution, you can see there's not a whole lot of molecules or ions that are dissolved. Where on this side, you can see that a bunch settled out at the bottom. Then you know that that is a saturated solution. Now, what are some of the things that can affect the solubility of these? This is just looking at standard room temperature. If we just dump it in, stir it around, and see how much you can dissolve. Things that affect how things can dissolve. One is temperature. Raise the temperature. In general, you raise the solubility. You know, there's some freakish ones out there that it's not the case, such as looking at this chart, sodium sulfate, it actually decreases as temperature goes up, so that one's kind of freakish. But most of them, the solubility increases as the temperature increases. And you probably have all experienced this. If you're heating some sort of liquid on the stove, let's say, you know, you're heating milk or water or something and you have to dump in some sugar or salt, and it doesn't dissolve right away. But as that liquid starts heating up, then the sugar or the salt or whatever can dissolve more readily. So as temperature increases, solubility increases. For gases, it's the opposite. And I'll go through that in the next lecture. But let's just look at this one. So we can start looking at the relationship between temperature and solubility. Now notice for the solubility curves, it is out of 100 grams of water. We're looking at the grams of solute in 100 grams of water. You're going to be using these solubility curves to do some calculations. There might be some questions such as, what's the solubility of glucose at 40 degrees? Here's 40 degrees. We look at glucose, being able to follow it on up. There's the solubility. That is right up. What the lines represent is the saturation point. We can say it's about 130. So that means you can dissolve 130 grams of glucose in 100 grams of water at 40 degrees Celsius. Some other examples would be how much would not dissolve if you had a temperature 20 degrees for sodium chloride and you added 60 grams. So let me say that again. If we add 60 grams right here of sodium chloride, here's sodium chloride, add 60 grams of sodium chloride at 20 degrees. How much would not dissolve? First you got to figure out what is the saturation point. I'm going to call that, I don't know, 39, 38, 39. How much would come out of solution? About 21 grams would not dissolve. If we add 60, subtract out the 39 to get our 21. Let's take a look at this learning check. At 40 degrees, you're told the solubility of potassium bromide. Now, for A, B, and C, we're going to determine whether or not these are saturated or unsaturated. The first one, we're still in 100 grams of water. We're still at 40 degrees. That was what it was originally given to us. 100 grams of water, 40 degrees. Saturation point is at 80 grams, and only 60 is added. Therefore, this is an unsaturated solution. How much more could you add? Hopefully your answer is 20. You could still add another 20 grams of KBr, and it would dissolve. Let's look at the next scenario. Now we're working with 200 grams of water, so it's double of what you're given. At 40 degrees, temperature is the same. If you double the amount of water, you should be able to double the amount of solute. Originally it was 80 grams in 100 grams of water. Now we could dissolve 160 grams. So if we look at how much was dumped into the water, 200 grams, this would be a saturated solution. So I could ask you another question of how much would not dissolve, and that would be 40 grams. The last one, we're dividing the water in half. You divide the solute in half. The maximum that could be dissolved is 40. You're only adding 25, so this is an unsaturated. You could add another 15 grams for it to be saturated.